So I'm going to give the introductory kind of setting the stage for what I think of as congested subduction. I'm speaking on probably for myself and Pete. This is a talk that Pete and I sort of have put together and share, but it also contains a bunch of stuff from Dan pertaining to flat slab, things that he had worked on, and some work with me. Just a lot of general stuff. So I think it's reasonable as a sort of an introduction. And those of you who came to my RSES seminar, you probably recognize 99% of the slides are the same thing, but it's a good reminder. Okay, so I'm talking about in terms of numerical models and giving an overview, but almost everything that I'm going to talk about is sort of about what we mean by congested subduction and why we think it's important to understand the congested part of subduction and contrast it with the regular mode of subduction. So let me just march on. The movie that I'm showing here, I'm standing in front of, is what I think of as a perfect example of congested subduction, some buoyant material that is being ingested into the subduction zone and causing a change in the balance of buoyancy or the behavior of the plate boundary system in general. So, you know, the plate boundary megathrust has got material that's now anomalous compared to elsewhere. Okay, in that sense, it's sort of congested, and this is an inevitable result of the fact that the subduction zones are kind of a vacuum cleaner, garbage dump of plate tectonics, right? So all the stuff that's on the oceanic lithosphere ultimately probably finds its way to some sort of convergent zone. That's sort of the purpose of those things. And so ultimately, that's what you expect to see, that they will be continually trying to digest that. If it's an enormous block of continental material, then that congestion takes place in the form of a continental collision. If it's a seamount or something smaller, then you have some reef anomaly. Okay, so if you go to Wikipedia and look up what a convergent boundary is, you will find one of the cider projects actually that the group did in Santa Barbara 3 or 4 years ago. Are you there for that one? I remember. So we sat down and we updated a whole bunch of things on Wikipedia that were kind of misleading or weird. And all the students and postdocs sat around and said, let's do them. And one of them was convergent margins. And so these things are kind of like the accepted view of a fairly large group of people as to what a convergent margin should look like. And my point in showing this this particular slide is to say, well, these are really cross sections, and the view is that the important part of a subduction zone is to look at it in cross section, try to understand it. Okay, and I'm going to argue a bit against that. Yeah, I'm going to argue a little bit against that. Not that it's irrelevant, but that we can take a different picture. Why do I think that might be problematic? Well, because a lot of the things you then do is to look at a system like this and go, well, there's all these little pieces of the jigsaw that make up the subduction zone. So now we can try to understand the dynamics of this. And so we can look to see what happens when some material that's anomalous enters this system, and we can look again at what the dynamics of that system now looks like. And so if you do that, then you'd say, well, that's fine. If it's something like the India-Eurasia collision, then you would look at it and go, well, there's this huge block, so I'm just going to go down the middle of it and look and see, well, the buoyant material won't go down, kind of understand what's going on, right? But as you know, that's probably still a mystery after all these years of studying collisions like that. We still can argue and publish nature papers and things about why that collision is ongoing and what are the driving forces. Okay? For a small seamount, though, you can imagine the problematic part of particularly cross sections for a small seamount, and it goes into the subduction channel, disrupts everything, and you look at the buoyancy balance and say, well, there's all this buoyant material, so that's going to stop subduction. So the possibilities are it stops subduction in some way, or subduction continues. And there really isn't sort of a way, there isn't sort of a middle ground, right? Because you're assuming that you understand everything by this two-dimensional cross-section. Okay, so this is something that introduces what Dan was talking about, and that is that that if you do those, you can also look at those cross sections and try to argue that you understand the dynamics by looking at perhaps the shape of that subducting system, and we're going to talk a little bit about that. If we're trying to understand the stresses in these systems, we do need to understand the difference between pure elastic behavior that you see, well, that you very often see in a textbook description of how to understand the dynamics of the subduction zone. And an elastic plate is characterized by a particular property, which is that if you bend it, the curvature tells you exactly what the stresses are. Whereas in a viscous system, it also depends, well, it's a rate-dependent process. It depends on the pathway to getting into that shape as to how the stresses are, the pathway and the speed at which you get into that shape as to what the stresses now look like. And when you look at the geometry of, I've got my phone pointer today. When you look at the geometry of something like this, there's a big difference between the sort of conveyor belt subduction mode in which material goes in, turns a corner, and comes out the other side, in which, you know, this is basically where all of the strain rate is happening, and then it goes through a sort of, you know, constant curvature zone where there's no change in the strain rate, just translation, and rotation, and then does the same again on the sort of unbending side. You can compare that to something like a fast rollback system in which this is a typical particle trajectory, right? That's not following the shape of the subduction zone at all. These should have very different stress patterns in them. Okay, so it's important when we do these stresses to think about the change of shape. And as soon as you do that sort of thing, you want to think, really want to think in terms of three-dimensional things. All right. I don't want to spend too long on talking about this, but from a modeling point of view, we do need to just have a sort of a language in which we understand what are all the components of that kind of a system. All right, and so typically we have a group around the table with sort of a mixture of backgrounds, right? So from a seismological point of view, think of the world mostly as being elastic with some, you know, loss, right? So some viscous terms or something that dissipate energy somewhere, you know, whatever. Global geodynamicists think of the world as being a big viscous blob with some perturbations where there's some elasticity here and there that we don't necessarily need to worry about, like the crust because it's so small, and some compositional variations, you know, details. People who are in the tectonics field probably mostly worry, or very much worry, about elasticity and the behavior of faults, and you know, some viscous relaxation and some complexity of those interactions. Okay, but they are all the same. They're all parts of the same system, and so to model these, we probably need to try to understand what all those things are at once. Okay, so typically we can write things in terms of the bits and pieces we need in a jigsaw puzzle. We need to be able to do a stress balance. That stress balance needs to be, we can either write it from an elastic point of view, or we can write it from a viscous point of view. If we write it from a viscous global modeling point of view, which is where I'm sort of coming from, then we have to account for elastic terms as well, and they would come in as sort of force terms that are history dependent, that are sitting around in addition to buoyancy terms. And then the stress balance through viscous forces is the sort of primary driver. We want some form of mass conservation or volume conservation, and incompressibility is a sort of extreme end member, but it's actually hard to deal with, so we can leave that. I mean, it's hard, it makes life harder. That'll work. We need thermal evolution. I'm not going to dwell on any of this. Okay, and we need to deal with the complexities of the rheology, which needs to include some viscous terms, some elastic terms, and something to do with plasticity, which has many different meanings depending on your background, I'm afraid. Okay, so it could mean basically it's sort of it's a term that has sort of has the units of viscosity, but is highly nonlinear and often has yielding behavior and stuff like that. So from the point of view of a global model, plasticity might mean a collection of faults in the lithosphere means that there is a limit on the maximum stress the lithosphere can support. Okay, from a mineral physics point of view, it might mean the deformation of crystals by dislocation movements. Right? From an engineering point of view, it might mean something quite different again. So there's a language issue that we sort of worry about, but often what we're trying to do is represent the different bits and pieces that we see in the system. Some sort of primarily viscous behavior that relaxes stresses on a long time scale, large spatial scale, some sort of elastic stresses that are important on a potentially a shorter time scale, maybe much shorter time scale if you're a seismologist, but which are sort of subject to interaction with these viscous forces, and then some kind of yielding type behavior where things, I've written this as being strongly anisotropic, where things will suddenly change behavior as a result of a transition. You do that, you've got quite a lot of the ingredients you need to do sort of models which include the mantle and the lithosphere as well, right? So you can do that. You can in principle do those things. And yeah, okay. So then it's not a jelly sandwich. It's a what do you call those things? I can't remember. There's chocolate on the top. Anyway, it's pretty good. The top part is, what did you call it? Caramel slice, I think. So very brittle at the top. It has a behavior that cracks dominate, viscous in the middle there, frictional granular material on the bottom, and you need all the bits to model that. Okay. It's all right. So we put all those together, and we need to model them all at once. And there are some subtleties in having to model all these things at once. One of them is that a lot of the things like all the assumptions you put into making models of, say, mantle convection are that you're dealing with a fluid and that the fluid has very little in the way of history. And that's kind of that's how fluid dynamics works. You worry about the parcels of you worry about the fluid itself, not the individual molecules of that fluid. Right? But if you embed a material in that viscous fluid that's got some elastic stresses in it, and those stresses are relaxing, so you bend something, bend some elastic beam, you throw it into syrup and you watch it unbend, then there is a history for those stresses, and that history depends on orientation as well. Right? So if you put it in one way versus the other way, those stresses are going to unbend into their original configuration. So your assumptions in the fluid dynamics kind of extreme end member is that it doesn't really matter what one piece of fluid is exactly equivalent to another, and in the elastic end member is that you're very worried about the stress history of each individual parcel of material. And so those are sort of actually quite hard to reconcile in terms of modeling, and that's why it is actually that people model the lithosphere with specific lithosphere codes and the mantle with specific mantle codes. And only in the past few years have people really started building codes that do the whole system together. In order to do that, you've got to be able to track both the very, very large infinite strain and the very, very kind of elastic small strain limits. So we do that by considering how, by writing sort of your particle, you have to worry about where it's been and what orientation it's being in. And if you're really getting fancy about it, you worry about the deformation it's undergone in each small part of a trajectory. You know? And it seems like that's a complicated thing that I've just talked about. But actually, you can think about it in terms of what calculus is really about, which is taking limits of differences of things and taking those limits in an appropriate way. Okay, so when you learn your calculus for the first time, you always say, well, it's sine theta plus delta theta and all that kind of thing, and you work out what the limit's going to look like, and you come out with cos theta, right? But you don't have to. You just go, well, actually, we've got this thing, we've got something similar at a previous time, and we can do a sort of a finite difference. We would want to take the limit. With a computer, we never get around to taking the limit anyway. We always make it some finite thing. So when we're modeling, it's probably more useful to think about things in terms of these little finite changes. Okay, and in the relevant finite change you want for a parcel material that's moving is actually the difference in the stress now compared to what it was for this particular parcel material a little bit of time ago. Actually makes things much simpler because you don't have to worry about what the complicated calculus of that problem is. You just have to worry about sort of, can I trace back in time a little bit or trace forwards in time and store my current conditions, and then I can do a difference later. So I worry about whether it rotated a little bit, I worried about the fact that it translated a bit, but really, as long as I track back properly, I track time properly, and I store the stress, I can do a finite difference very, very easily. It's much easier to think about than what I was trying to show you in the previous one, which is if you do that by classical calculus mechanisms, then you have to do a full material derivative. You have to worry about rotations. You may even have to worry about deformations. Okay, so that's the sort of what happens if you just launch into your math textbook way of looking at it. And then you have to do finite differences on that, or you can just kind of go back to what it fundamentally means, which is I moved something, it had some stress, and I'm going to record what that stress was. That observation actually has led to a lot more of these very general methods for modeling both the lithosphere and the mantle. And here are some sort of things out of the museum of modeling that show you the kinds of ways that we do stuff. Right? We have a classical fluid dynamics code, but we actually track things through that mesh. Okay. Righto, that's not that one. And so just to get people's eye in, if you like, when you're doing convection models, this is what we mean by sort of infinite strain. We don't care. Stuff is moving all over the place very rapidly. So here is this is sort of a very old model again, but it's looking at some continental blocks and how they attract lithospheric, how they attract fluid dynamic instabilities. Those kind of fixed steps are sort of attractors for instabilities. It could be at the top, it could be at the bottom. This is actually one calculation, and I kind of did an oyster thing that cracked it open so you can see the top and the bottom interacting. But the point here is that it doesn't really matter, right? The stuff is just moving around, it gets hot, it goes cold. We're worried about the fluid dynamics of it, not what stuff is. But here's the other end member, and of course these are done with exactly the same modeling code of looking at, this is more like what Roman was talking about, looking at rifting, so extension of some layered material. This is designed to model a sandbox. So the material at the top has frictional type rheology. The layering is just colors in this case. The bottom is syrup type rheology. It's pure viscous material. And then I'm just showing everything behaving the same, but I'm changing the cohesion. It's not a purely frictional material, it has a cohesion. So it's changing the cohesion. You can see that the spacing of the shear bands, which possibly represent faults, maybe not, will change as we change the cohesion. We're changing sort of relative strength behaviors between the two layers, and then they interact. Okay, but in this case, it's extremely important that this part of the material has previously deformed because it starts to lose cohesion with more deformation. There's a feedback loop. And so we have to track all that. Right? Down here, we don't care, it's viscous, and all you can see is shading here is to do with the strain rate. Okay, so this is the model. On top of the model on the right-hand side is my interpretation of what those various things are, and that includes places that are not immediately undergoing deformation, but I have a history of deformation associated. And so I can interpret things slightly different. Fat lines versus thin lines. Okay, so the modeling is getting a little far from the pure congested subduction story, so we better get back. All right. In order to understand, the behavior of the lithosphere in response to subducting slabs, we actually need all those ingredients. This is a model that I'm sure Dan has updated since then, but it includes quite a few interesting things. That's on the left. On the right is some models from a few years ago of ours. These models have deformation, or a fluid-like deformation underneath, and they have a lithosphere. And what I'm showing you is tracking that deformation. So actually, they have quite a similar. They're quite similar to taking this kind of a model, but in the context of a subducting lithosphere. So scaling it to be much bigger, but it still has the capacity to form shear bands and still has the capacity for viscous deformation underneath. And so that's sort of how to understand what the ingredients are of a model like the one I was showing at the beginning. It's like this. These models are relatively low resolution, and on the left one is one of Dan Sandiford's models that is showing the potential of these kinds of systems to model very high resolution, to model this sort of shear band development and fault development in a system as it goes through the outer rise with the way down into the interior. Okay? So these are more about potential than they are about interpretation in detail. Okay. All right. Let's go on to talk about the three-dimensionality again. This is your traditional view and the cartoon. Showing you those again. And then here is a bit of history. If you actually look around the world at subduction zones, we obviously realize that they rarely have a shape which is well represented by perfectly two-dimensional cross-section. They mostly have a shape which has significant curvature, terminations, inflection points, you name it. All right, even in the sort of open ocean. So this work started probably 15 years ago. Looking at the Isabelline Mariana system, and the fact that this inflection point in the system is kind of a pinning zone with some anomalous buoyancy going down. And I guess if you look at the other end, you might say something similar. Okay, we can zoom in to see that. You have to do, it was important to pick your color scale to highlight what you're talking about. But at both ends of this system, we have significantly anomalous bathymetry, which means significantly anomalous buoyancy. And so that's pinning at both ends of this, the arcuate part of the system. Okay. Well, that's just a story. It doesn't tell you if you really understand it. But we see, this is really just picking some slides to point out that there are many places in the world where we see these kinds of interesting, highly arcuate geometry. I'd like to know, how does it get to be that way? What is driving it, and what is the dynamic evolution part? Right? We're also later going to talk about the Alaskan system. The Alaskan system is interesting because it's an ongoing example of collision. So we have the Yakutat block of anomalous buoyancy being subducted underneath this sort of the end point of the Aleutian system, and what a coincidence! It just happened to go in right at the end there where the big kink is, or is it cause and effect, right? So that's kind of where that's what the workshop discussion to some extent is going to be about in terms of trying to understand these systems. So is that a pattern that we see everywhere? So this is an argument we made in trying. This map is actually from the front page of our Discovery Grant application, and says, well, wherever you look around the world, you do see that there are these sort of zones of significant curvature, and more than that, we actually see that in many places we are seeing advance, collision associated with retreat. And so this, those of you who can see the colors, it's a little bit hard to see in the light here, but the orange parts are the sort of the obvious collisions. The turquoise parts are regions where there is retreat. Okay, so for every time you see a significant collision, it's combined with some region where the subduction zone is retreating. And somehow they're connected to one another. Okay. Through the same plate. So we argued in asking for our funding, we argued that this really is causal. Okay, that we do expect that the trench motions associated with anomalous buoyancy or anomalous, so having a sort of a long strike variation in the properties of the subduction zone. So that can also include variations in the properties of the megathrust, or it can be in buoyancy. It can also be in strength. It can also be in the lithospheric properties. That can be buoyancy or strength, right? As well. That these things are related, and it would be very interesting to understand the whole dynamic cycle of how subduction zones ingest material, what that does to their behavior, and how they recover, if they recover. So this is the work of, initially the work of Wendy Mason as a honors and then PhD student, working with Pete and Megan and myself over the years. And she did some very preliminary experiments, very similar, but basically very similar to the laboratory analog experiments that were being done. She was at Monash, Pete is currently at Monash. The analog lab at Monash is pretty active, and they were doing single slab subduction. It's like one hand tapping, right? But anyway, single slab subduction with no overriding plate, and looking at what happens when you put some anomalous buoyancy into that system. Okay, so a lot of work was done on the dynamics of those slabs, very, very simple systems that could be reproduced in analog models. So we did numerical models that matched the analog models, and then we started doing things that were a bit harder for the analog modelers to do, like gigantic suites of runs and very three-dimensional things. But what we saw was that when we put in anomalous buoyancy, we got trench advance. So there's the original position of the trench at the beginning of the experiment. We're subducting something along that line, and here is an anomalous part of the system that sees advance. It's associated with retreat. It's not too complicated to understand that. That's sort of a conservation of it's associated with conservation of mass. It's also associated with the fact that we're trying to ingest buoyancy. So this part of the subduction system is actually resisting subduction. This part is driving. Right? So once you start thinking about how that geometry has to work, we start to see this a little bit more clearly. Another form of anomalous subduction that we talked about in a separate paper is what happens with plumes interacting with subduction zones. Okay, so in traditional convecting systems, you don't really have upwellings and downwellings hitting each other all that often. It's kind of self-organized system in which they avoid each other. But there are sort of two kind of rules of thumb about how things work. One is that subduction zones tend to roll back, and the other thing is that hotspots don't move very much, right? So we've got those two things, and so that does tell us that if they're both reasonable rules of thumb, then we should get a system in which subduction and plume, subduction zones, subduction slabs and plumes should interact quite often, okay? Or more often than they would in a sort of a simple fish tank convection experiment. So we were asking the question of what happens when a plume head and a subduction zone start to do that interaction. And we viewed it in terms of this congested subduction idea that we had seen from modeling plateaus. So we argue, well, the anomalous buoyancy here tends to fight the subduction zone. So we start to see advance. The rest of the system retreats. That leads to the possibility of a plume crossing a slab without either the subduction zone stopping or the plume being destroyed. Right? In a purely two-dimensional argument, you can't really do that because there's an infinite slab and the plume is also infinite in some direction, in the same direction. So you have to do a break-off event. But in 3 dimensions, it's actually possible to create a window for some period of time, move the plume through, and then stop. Okay. So I argue then that if you just think in terms of 2 dimensions, the buoyancy balance and the strength balance that you're trying to work on is somewhat misleading. So in contrast to the picture that I showed a couple of times with things hitting the slab, here is the cross section. Some of it is off the top of the screen, but that's sort of, we can live with that, I think. The cross section is through this end of a 3-dimensional model with a very, very wide straight subduction system and a very sort of small oceanic plateau coming into that system. The collision occurs right here, and then subsequently we have ingestion of that material. Some of it is accreted onto the upper plate, some of it is ingested below. Okay, but the buoyancy balance between this material and the downgoing slab, etc., is more or less irrelevant, because when you start to look at this movie, which you get to see a couple of times, the buoyancy balance is actually between this small anomalous region and this whole subduction zone, right? So the whole subduction zone is still going. Of course, it doesn't care that it's got this little piece caught in its teeth, right? It's like, no, I'm just going to keep going. So obviously, if you do a 2D cross-section through that zone, you would say, well, there's all this anomalous buoyancy to worry about. You do the 2D cross-section anywhere else, you don't see it at all. So we really have to think in terms of 3 dimensions. And just skip the model setup. But you can, we ran those models many times, and we started to see a pattern which is kind of, well, it is simple, basically, that we have, when the plateau comes in, we had, sorry, let's just slightly take a step back. Initially, we can see that the subduction zone behaves like a 2-dimensional approximation is good for it, right? It doesn't really vary in any direction. Everything is set up very nicely. It's only when you have the collision occur that that part of the system gets congested and it starts to change. So what's really happening is that we don't really have a plate boundary there anymore. Okay, we create a perfect suture at the initial, at this zone, and we can look at. You probably would look at these things with in some detail, but there is a point at which we create a suture, and that's the point at which you don't really, at which this thing starts indenting at the plate convergence rate, right? If there's no plate boundary here, and there is subduction here, then it's sort of, plate kinematics tells you that this one has to be retreating relative to the other, right? So it's sort of you know, plate kinematics is good enough here to tell you kind of what's going on. We shut that plate down, we create the next one, okay? What we're also doing, and you can sort of, you know, you can follow this on this graph. Here is where the trench retreat is occurring. The green is the rate at which things are subducting right here, and the red is the rest of the system. Okay, so it's more or less, it's interrupted but not shut off on this side, and it starts to retreat. And here it basically shuts off completely. We have some kind of distributed plate boundary. But then again, then it restarts behind the system, and you see that it basically goes back to being a straight subduction zone. Maybe not quite straight, but much, it goes back to approximately a two-dimensional system. So we were able to follow the accretion of a plateau. Some of it is eaten. So you have the suture, you have the creation of a slab window associated with that. It's quite a small slab window. We lose some material through that. And then it recreates the subduction system again. And we've moved the plateau partially onto the upper plate. We've also got rid of a bunch of its material. Okay. And it does matter what the size of the system is, because that buoyancy balance is about how much material, how much of this subduction zone is shut off compared to how much is still operating. And the only way to keep a system operating while a large-scale collision is going on is for this part of the system to retreat, very broadly, and then eventually it can start subduction again behind it. Okay, it's a small-scale case, not such a big deal. That is also true of how long the window is open and how much material goes through. So these are little markers, and this has now got out of sync, right? But the markers don't really make it through for the small plateau, but they start getting sucked through when you have this large system. You can see material that is being dragged through the slab window right into the other side. We did the same sort of thing for that example where we had the plume. The plume material underneath is not a true model of a plume, it's just material with anomalous buoyancy at the top and the bottom. And we were able to determine, or at least start to understand the fact that it matters whether or not you have anomalous buoyancy as opposed to anomalous strength in the, so the plateau tends to clog up the subduction zone, the actual plate boundary, and so it creates a very effective suture, whereas the purely a plume doesn't really create that suture, so you move into much more of a flat slab mode. Okay. Put the two together and it's quite chaotic, but eventually it does restart. Okay. And this is the model that yes, we can show. Yeah. This is the large scale suturing of a large continental ribbon coming into the system. You can see from this particular angle that we create very arcuate structures which are sort of which are the driving, which is the only way that this system, which is quite tightly constrained, can continue to release negative buoyancy out of the lithosphere to drive the system. Right? Got a big suture you've created, you're creating a big buckling of the overriding plate. All that is not contributing to any buoyancy that is the only driving force of this problem. Okay, so in order to have significant buoyancy to drive the system, you have very substantial trench retreat and even this very arcuate sideways subduction. Get them both together. Oh. Okay, this is sort of the view from underneath. So you can see the older, stronger lithosphere takes longer to form a window, more dramatic. And I think I'll just point out that in the shear banding that develops in the overriding plate is exactly the sort of Caponier escape tectonics model. Right? So there's some connection between the kinds of behavior that we see in these kind of systems and the more classical simplified models that we sort of start from as our guiding principles. Okay. Now these models don't have any thermal effects, and because they have no thermal effects, they don't have any magnetism, so they're missing quite a substantial chunk of the interesting story here. But nevertheless, there's quite a bit of the sort of the physical modeling that we physical models people have done in the past that we kind of combined. right? So we've kind of got, you know, Taponnier plus all of the, you know, the Roman subduction models or the Schlatt subduction models all in one go. And I just want to point out one other thing. These are quite constrained. The slab goes all the way across. So there isn't a reorientation as a result of the collisions. So we're forcing the slab to change its geometry, we're forcing the trench to change its geometry in these systems because the plate motion direction can't change. So they're sort of constrained in a very specific way, but it shows very clearly what happens. And the plate motion is also sort of, it's not constrained by any velocities, it's constrained only by the boundary condition. But you'll see that the motion is sort of in the same direction, despite the change in the trench geometry. So the subduction here is kind of, the subduction in this retreating subduction zone is simple retreat-like paths, but in this part of the system is also simple retreat-like paths. Stuff is going straight down. Even when you see the trench going sideways, material is actually going into the system this way and straight down, pinned at this end here. Right? So very arcuate systems may not be created by, don't need to be created by a subduction sort of somehow going in some weird radial direction. It just has to be created by the trench doing this and by the capacity for some sort of deformation in the slab that will accommodate it. And if you're thinking about this I start thinking about this from the point of view of where does the arc form in a system like this, because we have subduction only in this direction. So that's why we have this kind of, you know, thought experiment to talk with people about what arc magmas can tell us about congested subduction. It's not just about this part where you have sort of cessation of the arc and the creation of a window and all kinds of interesting stuff in the volcanic sense, but also what happens in these very arcuate systems where they might have got in place in a sort of very different style. So yeah, you can look at the movie if you want to and pick the trajectories of individual parcels of material. That's along that AA prime that I wrote in the movie here. It's off the top somewhere, I don't know. But anyway, that's along this path, and this is through time what the particles are doing. So they're just dropping. Okay, they're not moving sideways either, because that line is basically not moved sideways. So they just plummet in a very, very fast retreat kind of path. And some of them come sort of weirdly backwards. That's sort of a result of that pendulous chain of material that forms the bowl. So we see this kind of thing everywhere, and we argue then that the congestion story is told by many people, but the dynamics of it is that collision requires some sort of rollback for the to provide the driving forces, right? So this rollback that's happening is always going to be it's important if it's all on the same plate for continuing the driving forces. That's the buoyancy anomaly that is being subducted. And we'll overstress the lithospheric tension. Don't know if that's there as a break. So for those of you who are interested in the whole Tasmanide story, we tried to get into to tell this as you know, is there somewhere that we can see this whole thing having been completed, right? So the young end member is something like the Isobonin system or the Alaskan system with the attack collision. What do we see if we look back in time to something much older? And so we argued that we worked with Ross Cayley on his idea that the geometry of the oroclinal geometry that's observed in sort of Victorian system here is a result of the process, but a process very similar to the one that we modeled. So he came to that conclusion by looking at the geometry and the sort of the deformation indicators in the system and the potential field geophysics, we came to it by doing mechanical models, and when we talked to each other, we realized that, well, perhaps some of what we're seeing in our models will be applicable to sort of microcontinent accretion. So the models that I've showed you are sort of inspired by the original drawings that Ross Cayley had done, plus some of those initial things. We wrote this up. It's been quite well received, I think, and seems to stand the test of time in terms of broad scale observations. Not clear that we can interpret more than broad scale, but yeah, that's why we're here, to kind of put our sort of reputations on the line in that respect. I wanted to put myself in the crosshairs of people who do reconstruction, tectonic reconstruction, by just pointing out that we ought to probably change the null hypothesis for tectonic for plate reconstruction, which is, I think, the broad view, at least in the models that I see people present, is that if you have no reason to change the geometry of a plate boundary, you don't. Okay, so very often you will see collisions occur, and those collisions occur into a pre-existing ding, if you like. There's already a sort of waiting for the collision to happen. There's already a dent, and we would argue, well, that's not the way that we should view this. We should view this as the fact that the subduction systems will be straight. A collision will cause that curvature. There's real, reasonable physical reasons for that to happen. So your null hypothesis shouldn't be that, well, I shouldn't change the shape of this. You shouldn't be looking at what are the collisions, where are the places that are retreating. So that's a simple argument. It's not intended, and I don't intend to pick on Robert Hall particularly, although why not? Because it's recorded and you can view it. But if you look at some of these geometrical, if you look at the way that the things work in a traditional reconstruction, then very often you're assuming that the geometry doesn't change until it has to. But actually, well, I think that's right. But the collisions are the things that really especially change the geometry of the plate boundaries. And we would expect to see things like pinning in rollback and things like that being sort of quite important in the way that you should sort of approach a reconstruction. Otherwise, I mean, this is the place where everything gets eaten, and it's very hard to tell. So there are many places where you form transforms and stuff that it's kind of clear that should be sort of connected with the collisions that are happening and the buoyancy anomalies that are happening. So we sort of know why that should be, and we ought to be able to do that. So especially here's the lambda system. Start to think of that in terms of the way that forms as being far more associated with the endless collisions and rollback than anything else. Okay. Just want to ask Dan a question. Are you going to talk a little bit about the dynamics of slabs and the way that this appears in my diagram? Can't hear you. Still can't hear you. Looked like a yes. It's like a yeah.
Hi, Louis. Do you want me to talk to this slide?
I just wondered if you want hoping. Yes, you can. But I wondered if you were hoping to talk about this kind of thing, because next 2 or 3 slides are your flat slab story. If you're going to talk about it, I'm just going to skip over it.
No, you go right ahead. I'm going to talk a bit more about the Western Pacific, Kurils and Tonga.
Okay, excellent. All right. So I just want to. Okay, that's fine. Let me do that. Thank you.
Right. Thanks.
All right. So I'll return to this slide, and I want to talk about this really from the perspective of just talking about modeling again, the bits that went into those things that I showed you there. I said the importance of 3 dimensions. We've also done some work as have many others, on more high-resolution two-dimensional models, and looking to see what the best way is to try to represent the plate boundaries in such ways that they're resolution independent. And we do that in these models. We're doing that through some sort of interface damage zone, which is sort of inspired by observation, but also by numerical, by a sort of numerical methodology approach. And what we think that that produces then is, I'll skip that, is the capacity. So this is a resolution test. We can form models which are quickly convergent if we treat the plate boundary as a system rather than as sort of an emergent property. Okay, so we regard the plate boundary as being something that's really fundamentally important. Okay, to understanding how the models work. So it's something that has its own characteristics. And an example then is in the work that Dan did for his PhD, mostly on flat slab subduction. So it sort of starts to talk about very high resolution two-dimensional models, which we of course like to do as very high resolution three-dimensional models. But we are at the point, I guess, not just like us, but the community as a whole is at the point where not only can we start modeling the behavior of the lithosphere and the mantle, but we can also start modeling the stress patterns that appear in the slabs. We sort of see agreement between all the different groups who use different methodologies. And we can start to understand better how the lithospheric rheology actually looks and how it plays into the system. There's still a big debate about whether or not slabs should be purely elastic, whether they should be viscoelastic with some plasticity, how that relates to seismicity, and how it relates to the focal mechanisms that you see in slabs. Right? So this is something that we would like to be able to approach more as a simulation problem. And we would like to be able to approach that not in isolation, where we just model the slabs, but also where we understand what the interaction is between the overriding plate, particularly in flat slab subduction, where the overriding plate is interacting quite closely with the downgoing plate over quite an extended period, or extended region. And we can start to try to understand what the interaction is dynamically between those two things. And I think that although these are preliminary two-dimensional models, the work that Dan looked at was to say, well, we can actually start to look at the patterns of stress that the slab's picking up. And we can start to pick out whether it's really dependent on the immediate curvature or whether it's dependent on the rate of material flux through the pre-existing geometry, or some combination of the two. And in this particular case, looking at the sort of flat slab models, we found that it's very clear that it's dominated actually by stress advection and much less by the curvature that results from this. Is just there as the geometry. So it's not a purely elastic mechanism that is independent of the path the material takes to get into this shape. And that's really important if you're worried about where these zones are, where the stresses are reaching hazardous values, if you like, and then various things like that. So I'm not going to say anything conclusive. Yeah, Dan may be able to defend that, but what the point is that we are at the point, I think, with these kinds of models where we understand the very broad scale dynamics. We understand how to model the slab interface in various different codes in such a way that it produces appropriate behavior in the overriding plate, as well as subduction zones where the modeling is not, where the sort of modeling is not dominating, where the sort of input geometry from the plate reconstructions actually dominates what happens. And then we can start to interpret, as a result of that, we can start to interpret what the stress patterns are. And I know that if Gordon was here, he'd be jumping up and down about this because he has a view that the rheology is completely different from what we have looked at. But that's actually interesting because it does tell you something that that even though we can go measure rocks, we still don't know necessarily what the behavior of those things are when they're part of a more elaborate system. And even though we can go and look at the lithosphere at certain depths, even though we can look at sort of earthquake data in the crust, we still have some fundamental uncertainties as to how all those bits and pieces interact when you put them together. So I do want to finish on a more of an expansive note like that, than one in which I say, well, all the problems are solved. In fact, they're not. But we are starting, I think the people who are starting to do modeling and use these models to understand the geological settings of various places in the regions that are affected by subduction, which is many, many, many regions, right? The far field stresses are generally plate related. People are picking up these kinds of models and using them for real sort of geological interpretation. We need to understand what they're doing and whether that's correct, and how to be critical of these kinds of models. Right. So that's one of the things I want to kind of do in the whole story associated with setting this workshop up. Is here's one particular mechanism that we use for modeling subduction zones, one approach to it. We have codes for it. Rodri has a different approach to that. They are both sort of, we reproduce his results. I'm sure it works the other way around. And so we can feel confident that the sort of physics is kind of getting there. Now we need to sort of move towards, well, how does that interact with what the geochemistry is telling us? How does it interact with what the seismology is telling us? What is the behavior, and as a geologist using this sort of stuff in a way that is appropriate, let's say. And we also have a couple of people in the room, like Romain, who's responsible for developing much of the sort of this interface to allow people to use these codes. So I think he would like to hear what people are using these things for, how they should be doing it better, how he should be doing things differently. And I also wanted Romain to be here for anybody who does want to do some modeling with us using these techniques. He's one of the experts. So, okay, I would like to finish at that point myself, and I will answer some questions, although I think the whole workshop is supposed to be asking questions. Right, got one from Rodri.
Sure. I'm just curious, so at the interface between your different materials, you talk a lot about the interface. How do you treat that, so for example, in your 3D models, where you've got a slab controlling back, you've got a subduction interface.
Yeah.
And then an interface kind of naturally forms behind your buoyant block. So that's obviously dynamically evolving. Is there something different at the slab overriding plate interface to the back of that blob?
Yeah, so there is a little bit of a difference, and the difference is that in those, so the models that I showed in the three-dimensional case are at the sort of resolution limit that we could achieve, and the resolution limit is really around the fact that we've made that interface emergent from just the sort of material properties. So it kind of forms its own interface by chopping up the crust or whatever the layers are in the system. So the crustal layer is doing a double job. They're representing the crust, but they're also sort of, they need to be sort of dual purpose. They also need to serve as lubricating material for the interface. So we decided to break that out and say, when you look at these things, from my theoretical perspective, I look at it like a plasticity type problem. There is an observed kinematic behavior, which is that you have this zone in which there is rapid shear. It looks a bit like a shear band if you stand well back. But if you go close to it, it doesn't necessarily matter. It's not that it has a universal property. It's not that it's composed of sediments every time, or that a particular type of crust it's going down. Doesn't seem to matter what is being ingested. The behavior of the subduction interface is quite similar, at least from a mechanical perspective of this scale. Right? So you see something that has relative weakness and some things like that. Okay, so it's a sort of emergent property of the interface, or the interface is emergent, but it's not related to that oceanic crust of particular thickness going down. It could be mediated by damage, it could be mediated by composition, it could be mediated by the amount of fluids you get into the system, but ultimately, just like any shear banding problem, if you have some sort of feedback, you get a certain behavior. So we try to, instead of putting in compositions and variations and stuff, we put in that feedback. We track the interface in, and then we put in a sort of damage mechanism. And we say, okay, as you damage this, then we get this feedback process. It doesn't necessarily matter whether you damage it by hydration, or you damage it by weak sediments, or you damage it by something else, you damage it. And so that's the process, and that becomes rapidly resolution independent. So it seems like I won't say necessary evil, but it seems like an approach which is very similar to what we do for shear band. Which is to say, there is a feedback, I'm going to describe the feedback, not the shear band.
But at the interface originally, it's weak, right, because it's crusted.
Yes.
So that's what allows it to initiate.
Yes.
Whereas behind the blob,
yep,
it initiates itself.
It initiates sideways. It comes in from the pre-existing, subduction zone sideways. Goes pretty quickly.
That's where these feedbacks.
Yeah, and those feedbacks come in. So we haven't used we use those for the 2D models. We haven't used it to rerun on those 3D models. So that's a student problem.
You may have just answered this, but to clarify, in your models, the 3D models, the buoyant material is always accreting. Is that right? Always accreting.
You mean doesn't get?
It doesn't get dragged.
It gets a combination of accreted and subducted, and in the models with very, very substantial. I mean, we can make it so it doesn't get subducted. Very, very buoyant, very strong. Just basically, it forms a suture immediately. Yeah, you can. Yeah, you just make sure that it's anomalously buoyant. You can get most of it down. Some is always regurgitated, but I don't know whether you can have it. Unless you can do I don't think you can do something which has no side effect. If that's what you mean. Did we subduct a lot of material without ever knowing that? Probably the answer would be hard to do that. But little female.
Certainly there would be effects from it. But I guess I'm relating this. I'm always thinking about South America, and certainly this anomalous asymmetry that's being subducted. We're not seeing it accrete.
Yep.
In the models, what do you mean with that?
Okay, well, so I won't say these models are comprehensive. Okay, so the models that we did with, however, we did try to look at the difference between buoyancy, which is very close to the surface and therefore chokes the subduction interface as well as being buoyant, and material and buoyancy that's sort of within the lithosphere that doesn't affect the subduction interface, but does affect the buoyancy balance. And so if you do that, so if you have perfectly, the subduction interface is not affected at all, then what you see is almost no change in geometry of the trench. You only see change in geometry of the slab orientation, so it just goes flat. And we did see that, but I don't interpret that too hard because I'm not sure that the pieces that go, the ingredients that go into the model, some of them are rather contingencies to understand the problem, right? And so I don't think you should overinterpret that. But those are two end-member behaviors of that simplicity. All right, I'll go with Guidon first, just because I saw him first.
Just on the same topic, Mark Lewis wrote a nice paper with 5 days ago on calculations of what pieces subduct.
Yeah.
Did you test those scenarios?
No, we didn't. I'm familiar with the paper. I think it's the last time we talked. It's quite a while ago. But no, we haven't gone back to test those things. I think but they make perfect sense, because I mean that's where we're starting from in terms of setting up the lithospheric density structure in the first place. We're using those kinds of results. So I think it makes sense, but I haven't been back to check that. I think they sit in the that whole buoyancy. There's a little bit of difference in the 3D versus 2D buoyancy balance, which is, I guess, what we need to think about.
So in your 3D like simulation, do you really see like slab there, or just really show mostly I think it's mostly continuous a lot of cases. See this kind of phenomena, or
yeah, it mostly breaks off, but those windows that develop are really associated with the region of buoyancy anomaly, but they're also because that buoyant material is embedded in the otherwise strongest layer. Right, so it's in the coolest part of the slab, so they interrupt the strength, the strength part of the strength of the slab. So it's inherently a little bit weaker. But I think I tried to show that in. I'm going to do this. Let's try this. I tried to show that in one of these movies, which is this one, a pair of movies, which is the younger and yeah. So this is the region where the window is forming, right? So this stuff is sort of dementors come flying through where the window is formed, and this is a stronger, thicker slab. So it has the same buoyant material in it. And this one here has a more of a continuous strong layer. It does eventually form the window, but it's a lot slower, and you get a lot less material coming through, because by the time stuff starts to be able to come through, it's the retreat has already taken place a lot further back. Okay. So further questions should be via conversations over the next period. So there is now an opportunity to have a break, but we should decide who's going to talk after the break. And I think so Gidon would be a good candidate, I think, because you have a very general talk. But I want to make sure before we agree that, is there anybody who's online now who can only give their talk in the next hour or something like that? I don't know if that's the right way to view it. Go back to Zoom. Where's my other Zoom window gone? There we go.